All right, good morning. How's everyone doing? Well, thank you so much for spending your Saturday with me here. I know this is a very precious day with a beautiful weather outside. If you're in here, that really means a lot to me. So thank you for being here. I'm going to talk about something that's fairly exciting, and I'm going to talk about concurrency. For most part, I'm going to talk about actors, but I don't think it makes sense to talk about actors without really setting a stage for why we care about any of these things. So I'll talk about a little bit of introduction to why we want to get into this, and then I'll get into talking about actors. Best time to ask a question or make a comment is when you have it, so please don't wait till the end. Anytime is a great time for questions, comments. Don't hesitate at all. We are here to learn, we are here to share. There's a lot of stuff I don't know, so it's perfectly okay to ask questions and make comments. And if you do have a question or a comment, do raise your hand. If I don't respond, that usually means that I'm not seeing towards you. Even if I'm staring right at you, I'm probably not seeing you because my thoughts are somewhere else. So wave at me or just call out, draw my attention, and I'll listen to you. So let's get started. One of the things we do when we write code is we develop applications, and as we develop applications, from time to time we get dragged into writing code for multi-threading. Now, why would we ever want to use multiple threads? Well, it's kind of obvious. If we are in a server obviously has to support multiple threads. But what about applications? Normally, there are two reasons why we get into multi-threading or concurrency. One obviously is performance, but that's not always the reason, by the way. A lot of times we also do this for making the application more responsive, because the application may be doing something, a processing. In the meantime, the user wants to check on the status or want to interact or merely even move the application, and you want to make sure the application responds to it. Now, starting thread is extremely easy, but then the problem starts, isn't it? Well, let's give credit where it's due. What did C++ have before the time Java was? We had different APIs. Depending on the platform you had to code, you had to write different APIs. One thing Java did really well was it gave us one consistent API that we could use. It doesn't matter what platform we had to run the code in, because Java gave us this write once, run anywhere model. That's all great. But what are some of the challenges of concurrency itself? Let's talk about that. I want to talk about this with an example. Now, the example I want to start here with is a fairly simple one. I have an account class. Almost everybody here knows what an account is. Of course, every example is contrived, but let's look at this example. And what do I have in this account class? Well, in this account, I'm going to create a balance value within this account. And this balance value is going to store the current balance of the account itself as we are using it. And within this account, I have to perform two operations. I have a deposit method I'm going to write. And then, of course, I'm going to write the withdraw method. Now, what do I do in the deposit? In the deposit, as you would imagine, I check if the amount is greater than 0. If it is, I increase the balance value. And then, of course, in the withdraw method, I'm going to return a false if something was not right. And otherwise, of course, I'm going to check if the balance is greater than the amount, that we have enough money. And if so, I will reduce the balance and return a true. Otherwise, I'll return simply a false. And then finally, of course, the most obligatory get balance method, right? So how would we go about using this? Let's take a look at an example of using this. So here is a little sample class that is going to use the account itself. And as you can see, my computer is not responding very well. It's still recovering from the crash yesterday. So just bear with me as it takes the time to respond back. So what I'm going to do here is use the accounts. I'm going to create two account objects, and then I'm going to perform a transfer between these two accounts. How would it end up working? We'll take a look at it. So first of all, I'm going to use an account service object. The account service basically is going to be a service that allows us to transfer money between these two accounts. And how would we go about doing such an operation? Well, obviously, you want to take money away from one account, put money into another account. That's what you want to do, really. So how would we go about doing that? Well, we wait for this. Think about the thread safetiness of this code itself. Now, obviously, in this case, the account class is not thread safe at all. How would you make the account class thread safe? Any suggestions? I heard the word synchronize. That's correct. So you would normally want to make the code synchronized for this to work properly, right? That's what you want to do. All right, so how would I go about making this synchronize? I'm actually going to switch over here to Obviously, this is delaying me a lot more than I expected. So let me bring up my terminal here so I can work with it. Let's see if that will respond. So you want to synchronize this account. So where would you put synchronize? Obviously, in the front of the deposit method, I'll put synchronize. In the front of the withdraw method, I'll put the synchronize. But what about in front of the get balance method? Do I need to synchronize or not? Anybody thinks no? Or thinks not sure? I heard a few yes. Yeah? So why would we have to synchronize that method? Well, if I'm only getting the balance, I'm not making any change to it. Well, the reason why we need it is this. What does synchronize really do? Obviously, the first answer you will get from people is synchronize gives you the ability to perform get locks. Well, that is true, really, right? It helps you to get the lock. But there's a little bit more than going on other than getting the lock itself. Synchronize crosses the memory barrier. Now, what does that mean, crossing the memory barrier? A big word. Well, if you haven't had a chance to read, I highly recommend Brian Getz's book on Java concurrency in practice. It is one of the most scariest books written in computer programming. It is a book you read and you are shaking as you read the book because every page of it tells us things that we don't know about. When I read the book, I was scared. And as I was reading the book, I thought to myself, I could never write concurrency correctly if I had not written this book. If I had not read this book. After reading the book, I realized I cannot get concurrency right even if I read this book. That's how complex it is really, right? So let's see what the problem with that is. When you call synchronize, you are crossing the memory barrier, I said. Well, that is true, you're crossing the memory barrier. So let's talk about how that's going to work in a second. Now, what does it mean by crossing the memory barrier? Well, remember for a minute, let's take an example. Let's say we have this fine gentleman over here, and let's imagine that each one of us in this room is the thread, and he just wants to do some work. So what does he do? He gets up from his chair, walks up to the wall, let's say it's the memory, notes down a data and comes down and sits down and starts working with it. Let's say a few minutes goes by and he is interested in exactly the same data. So he's about to get up. Well, this gentleman, as being such a nice person as he looks like, he says, you know what, let's share this. And so they end up sharing the data together. Now, this is purely accidental, right? I mean, you didn't plan ahead that you're going to come and sit next to each other. Pretty accidentally, you're sitting next to each other, right? So this is like two threads running on a single machine. They end up running on the single core, and they end up sharing the cache. Now imagine a few minutes goes by, and this gentleman over here wants the same data. He is going to go to the memory and get it. He's not going to sneak over and share the data over here. So notice what's going to happen now. We got two copies of the data floating around. So in other words, in a single core processor, an application that is broken may pretend to work correctly. On a multi-core processor, the application may actually be broken really. Now, this is very frustrating, but I got an email from a person. I thought this email was very funny, but he didn't think so. His email said, I've got an application in production for the past 5 years, and it's running fine. And last month, my company got me a multi-core processor. I deployed this application on the multi-core processor, and all hell broke loose on this machine. And he went on to say, I know exactly what's the right thing to do, and I cannot. So tell me what's the quick fix. How do I make this application work fine on the multi-core processor? I wrote to him back saying, it's very simple. Walk up to this new machine and turn off all the cores except one, and your problem is gone, right? So the point is this, you cannot quick fix the problem so easily. So why is this such a problem? Because what happened here is, he's going to get the data from memory and not share with him. Why? Because in a multi-core processor, not only do you have multiple caches, you have multiple levels of caches. And until you tell the code, cross the memory barrier, take the data in the cache, and synchronize it with the memory. Hey, notice the word synchronize now takes on slightly a different meaning than the lock we've been using so far. So we are synchronizing the memory, meaning we are taking the cache and putting it in the memory, and taking the relevant memory data and bringing it back to the cache. And this crossing the memory barrier, by the way, happens several times in code. It happens, by the way, when you are calling the synchronize method. It happens when you are calling the volatile variables. It happens when you call thread.start. It happens when you are performing various other operations. And unless we know where all we are crossing the memory barrier, we could end up getting this very, very wrong. So I'm going to go out and say that 95% of applications out there are broken for concurrency, and we don't even know that. 95% of applications are broken. And you may say, what about that other 5%? Those were written by Brian Getz. They're okay, right? All the other applications are broken. And so it's very difficult to get concurrent applications running correctly. So if I go back to this code, and if I were to put in synchronize into this, what would happen? So essentially what's going to happen really is that the code would have synchronize in these different methods we are talking about. But unfortunately, though, the problem is it is going to provide a locking and unlocking. But what about the transfer method? In the transfer method, obviously, we're going to perform a withdraw on one account and deposit on another account. How is that going to work? So you have to put synchronize around that block of code as well, isn't it? Well, okay, I'm going to put synchronize around that block of code, and once I do, what's going to happen? Am I done? Can we go home? What's wrong? That's right. Oh, absolutely. So he's saying there's potentially a deadlock situation on our hand at this point. Not only could there be a deadlock, there are situations where there could be a live lock as well, right? That's correct. So granularity is really a problem. That's what you're saying. And you got to really be careful where things are changing and how things come together. So once you go about to fix that, what would you do? You would say, oh, I got to fix concurrency on that part, and you start putting locks in various other places. Now you got locks everywhere in the code, and the code has suddenly become more complex. Now here's the question. After doing all of that work, is your code thread safe? At this point, you're no longer sure, isn't it? You're kind of staring at this code. The other day, I wrote a piece of code. I had synchronization in there. On the way home, I thought to myself, is this code thread safe? And I was not sure anymore. I run home, look at the code, and sure enough, I had synchronized in the code, but it's not thread safe at all. And I'm like, oops, that's really broken, isn't it? That's kind of scary. And once I found out what the problem is, by the way, I went back to fix it. And once I fixed it, I said to myself, where else the code is broken and I don't know about this, right? So it's very unnerving when you have code like this that ends up being broken and we don't even know where it's broken. So that is basically where the problem comes in, is the code becomes extremely hard to work with. Now, how do we solve all this problem? Well, we could get down to synchronizing and suffering with all these things. And so I want to call this model as the synchronize and suffer model. That's what I give a name for it. Or there is a way to solve the problem. Now, let's summarize this for a minute. It is not that we have to put synchronize in code that bothers me. What bothers me is that if you don't put synchronize, your code becomes rather very unpredictable, isn't it? You don't even know that the code is broken, and that is where the real problem starts coming in. As you can see, this computer just doesn't want to respond anymore. I'll move a little bit further and see if I can get to the other issues as we go through. So the perils of concurrency really is that we are dealing with shared mutability. Now, on one hand, we are used to mutability in Java all along. We mutate variables all the time, so it's nothing new. But what about sharing? Well, sharing is a good thing, right? Remember what mom told us, share, that's a good thing. So we got sharing on one hand, mutability on the other hand, and independent of each other, they don't seem to be really as upsetting. But shared mutability is devil's work. And the minute you bring in shared mutability, you got to worry about how these threads are going to come together and how are they going to manage with each other. That becomes extremely painful to really handle. So how do you deal with this situation in code? One of the ways to deal with this is to use what is called managed mutability. And this is software transactional memory. We talked about this a little bit yesterday, but let me reiterate what STM is all about. In software transactional memory, what we do is we have a special type of variable called a managed mutable identity. This was introduced in the JVM through closure, and this is a reasonable approach to think about before we consider actors themselves. And what we do in STM is we have a variable which is mutable, but this is an identity, not a value. In STM, the values are immutable. You cannot modify them once you create them. But the identity is managed and mutable, and the identity points to a certain value. Now imagine if I ask you what's Google's stock price at 1 o'clock on Friday, you would say that's some crazy value, $950. What is the value at 1:10 in the afternoon? Well, that of course changed to another crazy value. Well, that's one way to look at it. But if you really think about it, Google stock prices never ever change. At 1 o'clock on Friday afternoon, it was some value, and that value is historic. Never ever going to change. You can come 20 years from now and say, what's the price? And it's always the same. So the price at 1 o'clock is the same, and I'm referring to it. At 1:10, it's a new value that we have, and I can flip the switch and point to the new value rather than pointing to the old value. In other words, the values are immutable, and we have the identity pointing to new values as time goes on. So if the values are immutable, how many locks do I have to put on the values for me to give that object to multiple threads? That's right, 0 locks. Because it's immutable, nothing is going to change, so no locks are needed. The identity is mutable. We got to be careful about it. But because the identity is mutable, as we flip the identity, we got to make sure it's thread safe. But that's where managed mutable identity comes in. And because it's managed mutable identity, the beauty of this is it knows how to manage this. And if you make a change to this identity at runtime, it will give you an exception right there saying, you are violating a transaction because there's no transaction actually running at this point. So it gives you an illegal state exception, no transaction running. And you get a very clear exception. Now, this is very different from synchronize because in synchronize, you don't get an exception at all if you forget to synchronize or synchronize at the wrong place. On the other hand here, you get a very clear exception saying that it's broken and you cannot really touch this object. So you would start putting transactions around it. And the minute you put a transaction around it, what's going to happen? Because you have a transaction, once you enter a transaction, think of a transaction as a cone of silence. Your code is running within this cone of silence. Any change you make is not known outside because it provides the as-see property of ACID property, is atomic, isolated, and consistent. And any change you make is isolated. And once you leave the transaction, when the transaction commits, the change you make is seen by the other transactions. So if 2 transactions are concurrently running, if one transaction is changing one object and another transaction is changing another object, they both can run concurrently and commit. They don't have to wait on each other, and no explicit locks are being held. But if 2 transactions are competing for the same object, one is making a change to it while the other is trying to make a change to it, STM keeps track of a change graph and keeps an eye on what all this particular transaction, this particular thread is changing. And if one transaction modifies an object and commits, it immediately goes to the other transactions that also rely on this object and say, I'm really sorry, if you run to completion, you will not finish, and it rolls back the transaction automatically for you. And as a result, the transaction goes back to the beginning, refetches the data automatically, and retries it without us doing any work at all. And as a result, we have a very secure managed transaction, and so we can safely have shared mutable variable as long as the mutable variable is actually managed. Now, of course, for this to work properly, we got to make sure everything is immutable except a managed mutable identity that we use in code. So shared mutability with managed mutability is actually a fairly good option to consider if you want to consider it that way. That's not a bad idea. But having said this, we want to also think about an alternative way to deal with it, because not everything would fit into this model of shared managed mutable identity. So another model that we have is called an actor-based concurrency. Now, I want to define, consider this as a word of isolated mutability. So we said shared mutability is evil. And what are the options? One option I said is shared managed mutable identity. But for that to be useful, we got to be very careful, right? We don't want to have mutable variables in the code, and everything we use must be managed mutable identity that we do want to modify. That is something we need to really consider. But as an alternative, what we could think about is, we could think about a situation called isolated mutability. And this is where actors come in. So what is an isolated mutability, by the way? An isolated mutability basically is that it is not like encapsulation. What does encapsulation tell us? Encapsulation says, I got a field, and I have hidden this field from direct access. If you want to talk to this field, you got to come through these methods to access it. That's what this particular approach tells us, right? That you got to go through and call these through these methods. But so you cannot talk to the variable directly, but you can talk to the variable through these different methods if you are interested. But what if multiple threads call those methods at the same time? Those threads will call to the methods will come to the variable, and now we have a problem with concurrency again. So I'm not talking about encapsulation. What I'm talking about here is isolated mutability. And now what does that mean? What that means is an object contains state, an object contains variables, but these variables are isolated, meaning no two threads will ever be able to touch this variable at exactly the same time. How does this really work? Let's think about this with an example. Let's say for a minute, this gentleman here has a phone number that he gives out to us, and all of us can call his phone, and many of us can call his phone at exactly the same time. Let's say for a minute that I call his phone, and you call his phone exactly at the same time. Well, obviously he's busy in a meeting, so he's not picking up his phone. So we could leave a message. Which of us is going to be able to leave a message? You can leave a message, or I can leave a message? Both. If you had a good phone company, absolutely, right? Both of us can leave a message at the same time. Well, notice how we were asynchronous. You and I did not block on each other or block on him. We just left a message and we moved on. This is called the fire and forget model. So you can leave messages and you can quickly move on. On the other hand, when he comes back from his meeting, he looks at his phone and says, oh gosh, look at all these messages waiting for me on my phone. I better respond to those. So he's got a lot of messages to respond. How many messages is he going to respond to at any given time? Only one, even though he has 2 ears, right? Why? Because he knows that multitasking sucks, right? And he knows that he cannot do many things at one time because everything messes up. So he gets one message at a time, processes that message, and then either finishes it or delegates it, and then moves on to the next message. Well, you understood what actor-based concurrency is all about. So essentially the idea is every actor object has a message queue that it waits on. And our other actors, other parts of the system can send messages to this actor continuously. And of course, this actor will pick one message at a time as it arrives and process that, and then it will move on to the next message as it comes across. So it can process one message at a time at any given time. How does this really help with concurrency itself? Well, the very first benefit of this model, of course, is that you are not going to have multiple threads modify a variable at the same time, right? That's not going to happen. That is the first benefit you get out of this. So no two threads are going to modify the object at the same time, and as a result, you don't have to synchronize this variable. In other words, the synchronization or the locking aspect goes away. Hey, but what about crossing the memory barrier? We still have to worry about that, right? Because the data may be used by one thread and another thread needs to get to it. Well, the beauty is when you send a message or when you pick a message, the underlying API in the actor library takes care of crossing the memory barrier. So we don't have to waste our time and effort asking, did we write the code properly? Did we cross the memory barrier at the right time? We don't have to worry about those things. Now, not having to worry about those things is a big deal. Why? Because A, there is less bug in the code, and B, we can devote our time and effort building applications rather than worrying about, did we write this correctly? Because writing concurrent code with synchronization is like walking on the street with the guy with the knife walking behind you, right? Every few minutes you kind of look over, am I safe here, right? That's not the way you want to program, isn't it? So this says, I'm safe. I can write code here. I know that the underlying API takes care of a lot of things for me. I don't have to worry about a lot of these different issues that I would otherwise have to worry about. So this takes care of a lot of things for us, so we don't have to expend our time and effort on this problem, and we can just fix it. So I want to get to the point where I can actually show you some code. So I'm trying to get to this right here. So let me restart this and see if it comes through. Otherwise, I may have to ask for your help again with your computer. So we'll see. I had an ability to run this morning. Obviously, I come and connect it here, and it doesn't want to run. So obviously, something is really wrong with the configuration here that I'm having trouble with. But anyway, so we'll see if I can recover and show you some code examples, because I really want to show some good code examples to play with this. Great. So now that we talk about that, how would we go about really using this? Let's talk about that. So I want to create a thread, an actor, and play with it. So how would this go about in real life? So the first example I want to use here is going to be pretty much an actor. So how would I create an actor? There are several different libraries available to create actors, by the way. Now, this is one of the nice things about Java, right? You never have one solution that works. You always have like 7 solutions you can pick from. So there are quite a few interesting actor libraries available that you can pick from. And one such library is called Akka. And Akka was written using Scala, but you don't have to know Scala to use it. Akka does a fairly good job of providing a fairly fluent interface, so we can talk to it from multiple different languages. So in here, I'm going to show you how to use Akka, assuming I'm able to bring the computer up to show the code, from Java itself. And you can, if you're programming in Scala already, absolutely use Akka from Scala. And in fact, Akka becomes more integrated with Scala moving forward, so you can use it fairly readily. But if you're not using Scala already, you're not forced to use Scala for this reason. You can use Akka from within Java directly as well. That's not definitely a problem at all. So we can definitely do that. So what you can do is you can tie it to Akka, and Akka gives you a couple of different types of actors. One of the actors that Akka gives you is called an untyped actor, which is kind of an interesting name, but it simply means that it is just an actor that can process messages as messages are being received. I really think I have to go for your help if you don't mind. To the point where my computer doesn't want to respond at all. So sorry about that. So we'll use your computer and fly with it. All that I need is Java, and of course, if you have Akka on that machine, that'll be great as well. So, and I love pair programming, but pair presentation is even awesome. So come on over. All right. So essentially the idea really is that I want to specify actor, but actor basically, the idea behind actors really is that you want to have this, thank you, do you have IDEA on your machine by any chance, IntelliJ? Awesome, this man is God sent. This couldn't have been done any better, I tell you. This is awesome. So the only trouble is he's coming with me to the US tomorrow, because I have to go make a lot more presentations. How could I do it without him? So he's going to travel with me. So the beauty really is that you can deal with concurrency, there we go, in a much more effective way without the synchronize and suffer model. That's the real idea behind it. So how are we going to really do this? So let's bring up idea, let's create a little Java project, that's all we need. We don't need anything fancy at all. Very simple, we'll kind of write code along. So let's create a regular Java application, and then we can take care of path and all that later on, so that's not a problem. Just create a regular Java application, a little program with the main, and we can get going from there. So basically the idea really is, we're going to create an actor, and remember actors have their own message queue. So what kind of actor can we create to begin with? Let's start with something very simple, and then we'll build on a little bit more with examples along the way. So I want to create an actor to begin with. So let's create a new project, and so the new project is going to have just a source directory. We'll create a sample class in it, And then in the sample class, we'll just create a main for begin with, and then we'll kind of put more things as we need it. I definitely will need your help to know where the path is and all that, but just call it a some project, example project. There you go, that's good. And yeah. And make sure that's a Java project, yep. Excellent, that's good. So, does anybody have a t-shirt with the IntelliJ commands on it? We may have to grab your t-shirt as well in a few minutes. Be ready to remove your shirts. Just kidding. So, all right, let's close that. Put a window, command one. Let's go to the src directory. Yeah, src, just scroll down. Yeah, command N, and let's go, or control N. It's funny how you know to type the shortcuts, but you can never say it. Does it happen to you too? Right? So create a new class. We have to wait for indexing. All right. Ceremony, yeah. All right. So let me, don't go too far away. Stay right there. We'll create a sample class. Okay. So what am I going to do in this sample class? All right. Come on, come on. Let's do it. All right. So let's go ahead and make this font a little bigger so people can actually see it. Come on, go, go, go. Did you have coffee this morning? You did. You did not give some to the computer? No. Okay. All right. So where's the font? Where's the font? Yeah, right there. So there's the font. Let's make this a little bit bigger. Okay, 24. All right. No problem, no problem. Yeah, next one. Just, you need to create a new one. Just save as an example. Yeah. And then change that to 24. Is it ready? All right, perfect. Thank you. Excellent. So is it better? All right, thank you. Excellent. So let's remove that. This is, by the way, there's a name for these things. It's called IDE vomit. So remove those IDE vomits. I hate them. So what are we going to do here? So I'm going to create a little main method. We got to create an actor. So first thing I'm going to do is I'm going to go to actor system. Well, where's actor system? We need actor system. So I need your help in a minute. We're going to go ahead and click on the module and we're going to bring in Akka. So let's go ahead and ask for Akka's module. We probably have to include 3 or 4 files, but don't worry about it. We'll kind of bring them in as we need it. So you can see that it's purely just downloading Akka and using it. That's all we are doing. So where is Akka? All right, if you don't have it, just download it. That shouldn't be a... do you see it? All right, download Akka then. So we're going to create an actor, right? So the actor we're going to create in this case, isn't that beautiful? This guy is smart, really good. All right. Excellent. And then look at where the jar file is. Oh, it's not a place to stand. Okay. You found it? Is the jar file there? There you go. Wonderful. We need. Okay. Go ahead and go through where to find where it is. So local. Very good. Open that. Yeah, and then come down to lib, and then take Akka actor. Yeah, that should be enough. Let's start with that first. We need a little bit more, but we can bring them in as we need it, right? Excellent. So at this point, this guy should be happy to recognize it. Oh, indexing. All right. So there we go. We got actor system. Dot create. We're going to use create method on this. Excellent. So we said hello Akka. That's all we did, right? And we got an actor system. And then I'm going to say actor system over here. Actor system dot actor of. And actor of what? We got to give a new property. So we're going to give a property. Let's give new props. And what's the property name we're going to provide for this guy? Well, we need an actor. Where do you find actors, by the way? Hollywood, of course, right? So Hollywood actor. And dot class. That's what we're going to create. And once we get an actor, we're going to get a reference to an actor. Let's give an actor name. Johnny Depp is an actor that my children like, so I use his name. And we're going to ask Depp to act a role. So we're going to tell Depp, and what are we going to tell him? To act the role of Wonka, right? And we'll ask him to act the role of Wonka. And that's my first message. Very simple, right? And then, of course, when we are done with it, we'll tell the actor system to shut down. Am I making sense so far? Yeah, so far so good. Let's go ahead and create the actor, by the way. So here is the actor class. And in the actor class, what am I going to do? I'm going to just tell the actor to implement this method, this interface. So implements this untyped actor. So untyped actor is what I'm going to implement. Well, where is untyped actor coming from? Let's make sure I'm getting this untyped actor really correctly. So untyped, there we go, actor. So now that we got it, I'm going to implement this method called onReceive. And what does onReceive do? It takes a message. I'm going to mark it final. You don't want to mess with the message itself, but you also want to make sure the message itself is immutable, by the way. All right, great. Now I'm going to only display playing the role of, right, the role of, and I'm going to simply display the message that we received. Make sense? Okay, great. Let's get back to the code and see if we can run this stuff. So, did I make a mistake? Oh, this is a return value. That's kind of interesting. I want this to be a void method. I don't want it to return anything. That's kind of interesting how it pulled up that one. I'm kind of surprised. Where did that come from? So untyped actor. So it depends on, okay, let's, fine. There we go, object. Normally, it would be a void method. So return nothing, right? So let's get back to using this. So how is this going to work? What's he complaining about still? What does he want? Interface expected here. Okay, that's fine. So let's go ahead and try this. So what am I going to implement at this point? Let's go ahead and run this code, assuming I have the keys correctly here. So what does this do? It creates an actor system, tells the Hollywood actor to go play this role, and apparently the shortcut key I used did not work. So let me try this one more time. So let's run this. That's fine. And what does it say? It tells us, oh, error. Okay, let's go fix it. It's not an abstract class and does not override some method. That's what he's complaining about. Let's understand what he is complaining about. You know what? I'm going to get rid of this for a second. We'll come back and do this again. So right there, let's go override the method on receive. That's what I want to implement. That's the method I would like to implement. And what does he want here? I'm going to simply output playing the role of, and let's message. So let's go ahead and run this again and see if it wants to run this time. Not sure what the error was. What is he complaining about? Does not override abstract method on receive on the class actor. Typically, by the way, this is a void method. That's what it is. And I'm really surprised that it was giving that message. So something is wrong with the library integration here, but we'll find out what it is. And Java class does not have option in it. So that's kind of weird. So let's see what the error is here is. It says cannot access Scala option. Oh, of course. Remember I said there's multiple libraries I need. So let's do it. Let's go ahead and do module. Let's bring in add reference to Scala jar that was in the same library as Akka was. So let's bring that. And while you're there, I'll ask you to bring one more thing as well. So go to the directory. There's a Scala sitting right there in the lib directory. There we go, bring that. And I need one more thing. Go ahead and go back to that same place. There's a config we have to bring in as well. and then look for libconfig. Keep going down. Yeah, oh, right there, config. Yeah, bring that in. Excellent, thank you, sir. Awesome. So now let's go back to this and play with this properly. Like I said, we had some kind of stupid errors in this case, but we'll fix it. All right, so that's done. Let's go ahead and remove that and see if that runs. Yay, look at that. So it says playing the role of Wonka. Awesome. I know what you're thinking. I could have written a program much simpler to put that word playing the role of Wonka, right? Got it. Let's try one more thing. Let's go back here and ask him for output. And in this case, we will say in main, and let's output thread.current thread. With me? Let's go to Wonka, the thread, and we will ask him to put one more message right here, by the way, plus from thread plus thread.current thread. Let's run this code now and see what the error message is. In the meantime, can we make this guy bigger, this guy here? So where do we go make that change? I want to make the font change so that it's easier to see that also. Console, do you see it? No, go ahead. Awesome. 24. Yeah. All right. Cool. So, hey, did you notice that? The main is in main thread, no surprise. But where is this guy printing the message from? Thread Akka Actor dash default dispatcher 5. Notice how quietly it switched threads. Make sense? So the actor is running it in its own thread. Let's try this one more time. We'll go back to this guy and say dep.tell, and this time we'll ask him to play the role of Sparrow, and let's see what happens in this case when we ask him to play the role of Sparrow. Run the code, and what does he tell us? And he tells us that it main ran in main still, but notice that two messages here ran in the same dispatcher-4 thread. So the actor is still processing the message in its own thread while the main is running in its own thread. Making sense so far? Let's do this one more time. This time, of course, I'm going to create a different actor. So let's go ahead and create another actor. We'll create Hanks over here. And now I'm going to say here, Hanks.tell, and let's ask him to play the role of Gump. And we'll also ask Hanks, in the meantime, after we tell this guy, to play the role of, let's say, Lowell. And in this case, I ask him to run this one more time. Let's try this. And what happens now? When I run this code, notice that in this particular example, we have the Wonka and Sparrow, you can see, running in the thread 5, and you see the other two messages running in thread 3. So in other words, both the actors are running concurrently, but one actor is running in one thread, another actor is running in another thread. Make sense so far? If we only stop here, it gives us the impression that actors hold threads hostage. And that's not going to be good at all, right? But fortunately, that's not true. Think of a thread to an actor as a waiter in a restaurant. If you go to a restaurant to have food, and you order food, but you should never invite the waiter to sit and have food with you, right? They kind of look at you and say, avoid table 7, right? So how do they work? They go buzz around and help multiple tables, right? So your actor is given a thread, your thread works with it, and if the actor has no message to deal with, the actor goes and does other useful work. And if a message arrives, another thread from the pool will be given to it. Just to see this is true, let's take a look at an example here by only delaying just a little bit. So thread over here dot sleep, And I'm going to just give a minor delay here, right? So I just gave a little minor delay, and what does it do now? If I run this, it proves the point. You will notice that in this case, that Wonka, by the way, is running in thread 2, and Gump is running in thread 5. Keep that in mind, 2 and 5. But later on, Sparrow and Lovell, remember Sparrow is the same as Wonka in terms of the actor, and Sparrow is running in what thread? Sparrow is running in 5, and Lovell is running in 2. Notice the threads switched. And the reason is the threads came to the actors and helped them, and looks around and says, look, the message queue is empty. And so I don't have to wait here and waste my time. I can go take care of other things, and the threads leave. And then messages arrive, and 2 threads arbitrarily came and started helping. What is guaranteed, though, is no 2 threads will ever enter an actor at the same time. That is where the managed immutability comes in. Am I making sense? So what we saw so far is how the actor kind of behaves. What I want to show you next is how we can put this to use. And I'm going to show you 2 different examples. One example is going to be to divide and conquer task. I'm going to take a very simple task, but it's going to keep generating more tasks on our hand. And I'm going to show you how we're going to put together this task in actors. And our goal is not to use synchronize at all in code, but get thread safety. The second thing I'm going to show you after that is I'm going to show you how we could use a typed actor, just to get an example. Let's start with this example before the break, and then we'll continue right after that. So let's get back to this code. Any questions on the actor so far, by the way, before we go forward? All right, please. That's a great question. The question is there a way to wait for a message process to be complete? A very good question. This is one of the challenges I face, is we need to deviate from our sequential processing life to a concurrent system that takes a bit of a design rethinking. And you got to deal with a few things. Imagine you give me some money and say, go get pizza. You want to wait for me to bring pizza, but you also have to enter into the thought that I may actually run away with the money and not bring you back the pizza, right? So you have to program for timeouts, for example. And to answer your question, you want to design your application where you send a message to an actor, and maybe another actor will get the result of it and process it. So it's a very redesign, and rather than thinking about sequentially as a waiting, deal with it that way. So let's look at an example of how we can use this. First, I want to give you an example of, let's say I want to go find files, a number of files in a file system. So let's write a little example. Let's call it as count files. So we'll say count files. And count files, by the way, is going to take a path as a parameter. So I'm going to just say path. And in this case, how do I go find all the files in this path? So I'm going to say file equals new file, and I'll give the path to it. That's great so far. And of course, I want to get all the files and count it, isn't it? So I'm going to say int count equal to 0. I want to return the count when I'm done. I'm just writing this code sequentially at this point. That's all I'm doing. So I'm going to say over here, let's iterate over the files. So for, let's say file, let's call it as child in file.list files. Well, it's possible that there are no files at all. So file.list files, let's call it as, is not equal to null. Then I want to do this, not otherwise, right? So we'll start with that. So what do I want to do at this point? I'll say if that is obtained, if the child is a file, then I will simply say count plus plus. If not, what do I do? Well, it's very simple. Count is plus equal to, and I can recursively call count files with the child dot get path. Am I making sense so far? So a very simple approach to call this, right? So I want to run this and see how much time it's going to take to do this, and I'm also going to run this to get the path. So let's say string, and I'll say sample path, and I'm going to put a path name here a little bit later. And then, of course, I want to call this and print out. So I'm going to simply say count files, and then I'm going to give the sample path over here. And we will measure the time for this. So we'll say long system.start is going to be equal to system.nanotime. And we will find the end of this also. So we'll say long end equals system.nanotime. And then we'll print out the time it takes. We'll say time taken, and then we'll print the time it took to do this, right? So in this case, I'll say end minus start divide by 1.0e9. So this is a good start. Now, what I want to do is see how much time it's going to take. But when we come back, I want to parallelize this. Now, why do I want to parallelize this? Well, you can clearly see that this code is sequential, right? But there's one more problem. It is recursive, and if the directory structure is too deep, you'll get a Stack Overflow exception. Make sense? But it is so much better to just parallelize this and say, here are my children, you go find the first child's tree, you go find the second child, and you can distribute it. But how do you make all these threads? And the minute you make the threads, you got to make sure all the results come back and you total them properly. It can quickly lead to a synchronization mess, isn't it? We're going to use actors to do that. So I'm told we're out of time right now. So we'll take a break. I'll start at sharp 10 minutes from now, and then we'll look at more examples. Thank you. Can you give me a sample directory that I can go recurse through? Not too big, but not too small. And we can run it quick to see how much time it takes. Something that will have maybe 1,000 to 10,000 files in it.